Yeah, good evening. Okay, hello. Um, Good evening, everyone. This is Manjeet, the TA for this course, Nature and Properties of the Material. Today we will do the assignment number 5, which is based on the ionic solids and their properties also. So today we will discuss one by one problem, and then if somebody has any problem, please raise your hand and unmute yourself and you can ask your query. Okay. Let's start, or we can wait for 1 or 2 minutes so that the people can join. I mean, let's wait for 2 seconds only, 2 minutes only. So let's start it. So question number 1 is the fraction of the octahedral voids filled by the aluminium 3 positive ion in Al2O3 is. So what will be the uh, octahedral void filled by the aluminium 3 opposite ion? You can see here I have Here I have put the Al2O3 structure where my O2 negative O2 negative form a hexagonal lattice, and this aluminium 3 positive occupy the octahedral voids. Okay, here from this one is this is my oxygen O2 negative, and my Al3 positive R ions are sitting it here, 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 and here, this one and this one and this one. This is my Al3O positive. Or other the ions are making the hexagonal lattice. 6 are on the top surface, 6 are on the bottom surface, and the 3 atoms are in between the to the plane, top and the bottom one. So you know that the HCP we have already discussed this. HCP has two octahedral words per unit cell, or we can say that one octahedral per atom. As this thing we have already calculated in the last tutorial, that maybe in the third or fourth, we have already calculated this thing, and we find out that the HCP is having the two octahedral words per unit cell and one octahedral per atom. So here this is aluminum occupy the octahedral one. So So HCP will be the now there is in the stoichiometry of Al2O3 we can see that there are the two aluminum ions, that is Al3 positive ion corresponding to the three oxygen ions. Now per atom we have the one octahedral sites. Now this is the three oxygen and ions here or the ions one. So we have one octahedral site per octahedral voids per atom. So we have the three oxygen atoms. So the total number of the octahedral void will be the that are available will be three because we have three now. But corresponding to 3 1 and the if you 3 1 we have only two aluminum ion, two aluminum ion. So the how we from this stoichiometry we can say that only the two octahedral site will be the filled. So number of the octahedral voids that are occupied by the Al3 O positive will be only the two because three are available. Two aluminum positive that are two aluminum positive are responding to with the three octahedral side. So number of the octahedral voids that are occupied will be 2. So now we have to calculate the fraction of the octahedral voids filled by the element. So total we have the 3 and occupied are the 2 1. So we can calculate the fraction. So fraction will be represented as the fraction of the octahedral voids filled equals to the number of occupied that are occupied by the aluminum ion octahedral voids divided by the total number of octahedral voids available. So we know that this is number of occupied octahedral are the 2 and total number are the 3. So the fraction will be the 2 by 3. And if I find out in term of the number, so it will come out to be 0.6666. So this is the number that is represented by the just a second. Hello. हाँ मंजीत, ये आपने कंप्लेंट नोट कर इसमें लिखा है ना कि वाईफाई नहीं चल रहा है। हाँ मैम। तो ये अभी आज भी नहीं चल रहा है? नहीं मैम, आज भी नहीं चल रहा मैम। ये रूटर है ना, ये ब्लू ही लाइन शो कर रहा है और मैम मेरी अभी मीटिंग चल रही है। अच्छा, आप कहाँ पे हो अभी? मैं रूम पे ही हूँ। मैंने अपने नेट से कनेक्ट कर रखा है, तो मैं बाद में या तो 8 बजे के बाद में कांटेक्ट कर पाऊंगी मैम मैं। नहीं नहीं, वो तो फिर उनके पास जाना पड़ेगा ना, या तो फिर मतलब आपके रूम के नहीं चल रहा है या फिर औरों का भी, पूरे फ्लोरों का नहीं चल रहा है? मैम मेरे फ्लोर पे मैंने मेरे साइड वाली लड़की से और सामने वाले से पूछ लिया है, क्योंकि मेरे को लगता है ये रूटर में प्रॉब्लम है, क्योंकि इसकी लाइट ही ब्लू जल रही है, क्योंकि जब चलता है तब ये ग्रीन चलती है। हाँ, आपके ही में ही प्रॉब्लम है ना मैम, क्योंकि हमारे साइड वाले में 3 4 लोगों में तो हमने देख लिया, इन सब में तो किसी में नहीं चल रहा है। तो मैं बाकी फ्लोर का भी मैं पूछ के बता दूंगी एक बार। अरे वो अभी अजय जी वहीं पे ही है ना, अगर कोई लड़की है जो कि वहां जा सकती है नीचे अजय जी के रूम पे, तो देख लेते हैं, अगर सर्वर से तो कोई प्रॉब्लम नहीं है। मैम पता नहीं मैम, एक बार मेरी तो अभी मीटिंग चल रही है, तो मैं एक बार एक लड़की और है जिसने डाला है नॉट वर्किंग। हाँ, एक बार आप उससे बात कर लीजिएगा, है ना? एक बार प्लीज। थैंक यू मैम, थैंक यू। So the this will be the fraction will be the So the fraction of the octahedral will will be by the aluminium 3 positive ion will be the 0.667. So C will be the correct answer. Okay. So this first question, in first question we have to calculate the fraction of the octahedral voids filled by the aluminium 3 positive ion in the alumina, that is the Al2O3, and we already calculated we have the available 3 number of the octahedral voids and 2 are filled by the aluminium ion, so the fraction will be the 2 divided by 3 because 3 are available and only 2 are the occupied one. Okay, so let's move to the question number second. In question number second, that is asked the what is the Madelung constant for the NaCl. So this is the theoretical question where this is simply you have to remember there is the formula related with the Madelung constant that we have to calculate. From that we can calculate this is something like minus iota raised to power Ni corresponding to basically Madelung constant represent your lattice energy of the crystal structure, which help to determine the potential of a single ion where we consider all the other atom as a I mean the point charge. So this is basically helpful to calculate the potential energy of the single ion also. So for the NaCl is come out to be around the 1.7. For I have test for the different crystal structure also. For the cesium chloride it come out to be 1.76. Fluoride is 2.519. NaCl having the 1.748 and the sulfurate that is the 1.638 and wizarite is the 1.641. Okay. So this is about the Madelung constant. So this thing you have to remember. Otherwise, the calculation for the this calculation is rigorous. This for this time you have to only remember this thing because it is not solved in the classroom and the professor haven't told about the for the whole derivation. So this is for only you can remember this thing for the I mean the for the standard crystal structure you can remember this one. Okay, so let's move to the question number 3 again. So now in the question number 3 it is asked if the radius ratio that is the R cation divided by the R anion lying in the range of the 0.025 in the 0.141. This is you know the for the octahedral radius and this is for the tetrahedral radius. Then you have to find out the then the coordination number of the cation. What will be the coordination number of the cation would be. So there are the different coordination number attached with the different radius ratio. If your radius ratio that we define radius ratio defined by the R cation divided by the R anion, if we take and if this is less than the minus 0.115, so my coordination number will be the 2, that is the my linear 4, and if this is lying between the 0.115 and to the 0.225, then my coordination number will be the 3 and my atom will be the I mean my atom will be the position like here. This is the positive, this red is representing your cation if they're cation and the 3 anion will be surrounded by this positive and there is the small gap between these two and as they are not touching here, there is a small gap between them. And if this radius ratio lying between the 0.225 to the 0.414, then the coordination number will be the 4, that is that the crystal lattice will in the position in the tetrahedral position, so coordination number will be the 4 1. And if this radius ratio is lying between the 0.414 to the 0.732, then the coordination number will be the 6, that the octahedral and you know the how the atoms are arranged in the octahedral tetrahedron. We have already discussed this thing. And if the radius ratio is lying between the 0.732 to 1, then the coordination number will be the 8, that represent your cubic symmetry 1, and that is for the CsClO1. And if it is greater than 0 or 1, so then the coordination number will be the 12, similar to the HCP, hexagonal closely packed, or CCP, the coordination number. Okay, so here in this question we have to find out the coordination that are lying between the 0.225 to 0.414. So this is the range where now the what will be the coordination number for this range. where the radius ratio lying from 0.225 to 0.414. So coordination number will be the 41. If any other radius ratio is given, then you have to find out what will be the corresponding coordination number for that radius ratio. So remember this one, for less than 0.11155, it will be the coordination number will be the 2, and having the radius 0.155 to 0.225, it will be the 3, and having the 0.225 to 0.414, it will be the 4, and it is greater than 0.414 and to 0.732, the coordination number will be the 6, and 0.732 to the 1, the coordination number will be the 8, and if it is greater than 1, and the coordination number will be 12. It is somewhat where the, I mean, how the my size of the cation is, if it is greater than an ion or it is less than an ion, or how, in what range it is having the radius one. So this is corresponding to how, then how my I mean, basically in lattice we have the different cations and anions, they are arranged. So how they are coordinated with this, for this for if we have the radius or I mean radius ratio, then we can for the sum of the crystal we have it predict I mean accurately, but for some of them it does not, that the professor have also I mean taught in the classroom also. So mostly for the most of the crystal lattice, it is giving the correct prediction for the coordination number. So remember this one, the radius ratio and the corresponding the coordination number one. So this is all about the in question number 3. Okay, let's move to the question number 4. Now in the question number 4, the fluoride structure show the 8:4 coordination. Now they have the coordination number in the ratio 4:3. Which of the following lattice have the fluoride like structure? So there are the three options that is given, and you have to find out which of the following lattice having the fluoride like structure. So now it is the this 8:3 coordination is already given, so we can find out the bone strength. That is, if we have the this is strontium exists in the 2 plus, and the chlorine is having in the C minus. So this will be the, if I'm calculating for this will be the 2/8, that is the my valency, and divide by the coordination number. Okay, for this one, if I'm calculating for this chloride, it will be the 1. This is giving me 1/4 for the chloride. It will be the 1/4 as well. So this is 1/1 by. So this CrCl2 will lattice having the fluoride like structure. If both are equal for the cation and anion, then they will have fluoride like the structure one. Okay. Okay, what happened to this one? Okay, there is something, what happened? Okay. Just a second, just a second. Okay, so this similarly you can calculate for the barium fluoride and the thioride oxide THO2 So for the barium also, it is having the, this is existing in the 2 plus F2, this fluoride is having in the -1, so this will also give you 2 divided by 8. This is 1/4, and the fluoride will be the 1/4. 2 divided by uh, okay, valency will be the 1 divided by 1 divided by the 4 1. Okay, and for the ferrite oxide will be the TS. This is existing in the plus 4 in the minus 2. This is 4 divided by 8, and this is 4 2 divided by the 4. This is 1 by 2, and this is also 1 by 2. So all of them are having the fluorite like the structure. This is the Cl2, and the different elements having like the I mean the having the form of AX2. Generally they are of the fluorite like structure. And these are the example. If the coordination in fluoride, they have the coordination number 8:4, and if I talk about the anti-fluoride structure, they are having the coordination of number of 4:8 coordination. Okay, so for this one will be the all of the above. I mean the SrCl2, BF2, TSO2 all are having the fluoride like the structure one. Something wrong. Okay, let's move to the question number 5. In the question number 5, it is asked, in NaCl structure, which of the following is true? Now you can now first look at this structure. This is of the NaCl where we have my Cl atom are occupying at the FCC arrangement of this one. You can see these are the at the corner one, at the face center. Similarly here also, and you here, and you can see this is the FEC are occupying the FCC lattice structure. Okay, and my Na positive are Na positive ion that are at the edge of this. I mean, if I am talking about this edge, so this is occupying at the edge center of the edge center of the lattice one. Here also edge center, edge center. So this Na positive, if somebody atom is occupying at the edge center, that will be the octahedral position, because it is the closely packed one. So for the closely packed, the octahedral position will be the edge center, and for the this tetrahedral will be the on the diagonal one. So Na positive will occupying the position of the octahedral one, octahedral position one. Now this is about the NaCl structure. Now let's move to the what are in the option. So in option 1, it is mentioned all the octahedral position are occupied. From this figure, you can also see the all your octahedral position. Here there will be the also atom. So this all are occupied one. Yes, so that this is true, though the all octahedral voids are the occupied one. Now in the what about the tetrahedral voids? The tetrahedral voids, as I already told you, that lie on the body diagonal one, but there is no atom on the body diagonal. So these are the tetrahedral sites are tetrahedral voids are not occupied. So this is also the correct statement. All the tetrahedral voids are unoccupied. So A and B are the correct. In C part, it is given half of the octahedral as well as the 1/4 of the tetrahedral void are occupied. No, all the octahedral voids are occupied, and all the tetrahedral voids are unoccupied. So this is not correct one. Let's move to the D part. This is in the D part. This is half of the tetrahedral voids are occupied one. No, tetrahedral voids are not occupied. So D part is also the incorrect one. So A and B are the correct answer for the NaCl structure. The octahedral will be the occupied one, and tetrahedral void will be the unoccupied one. Okay, so if somebody has the doubt until question number 5, then you can tell me. Then otherwise we will move to the question number 6 one. No? Okay. Then let's move to the question number 6 one. So in question number 6, it is said that the incorrect statement for the sulfurate, a form of the zinc sulfide that we have already did. This is the zinc blende. We also done this in the tutorial in the last tutorial also. The structure we have already discussed. And now we have to find out the incorrect statement for this zinc blade one. Okay, so this is the structure for the zinc one. If I see, who is filling this one? So this is the zinc plate structure one, where my zinc are at the occupying at the FCC lattice one, and FCC, I mean at the corner at as well as the center of the face one, and this zinc are connected to the sulfide. These are the red one are the my sulfide ion. This is the zinc 2 positive and sulfide 2 negative. Okay, so these are the, and this zinc is connected with the octahedrally one. So one zinc atom Zn2 positive atom is my tetrahedrally connected to the my sulfur atom. Okay, so in this part, A part, it is, and then its structure is similar to the diamond, except that the alternate atom are the zinc and the sulfur one. Yeah, it is true. In the diamond, we have the same like structure. There we have the carbon atom instead of the zinc and sulfur, and this is also, they are also having the FCC like structure, and the tetragonal they are oppositely my, this is the atom are not zinc and alternative. Here my atom are alternatively arranged as the zinc and sulfur. So it is correct. Its structure is same or more or less like with the diamond one. In the B part, it is said that the because the S ion is larger than the zinc ion, only 6 rather than 4 and 8 sulfide ion can be pegged around the zinc ion. Yes, it is true. My sulfur ion is greater than my zinc ion, but the only 6 rather than 4 NH sulfur ion. No, this my zinc ion is connected to the 4 one. If I see, this will connect, this atom will connect to the my 4 sulfide ion, because this is connected to the tetrahedrally to the my sulfide ion. So it will be connected with the 4 rather than 6. It will be connected with the 4 one, 4, that is the tetrahedrally one. So this is not correct one. The tetrahedrally they are connected. So if you see this one, sulfur is also connected with the 4 zinc. So this will also be, they having the same stoichiometry. So it will also coordinated with the 4 one. So this will be coordinated with the 4 sulfide ion. So as in the C part, as the C atom is larger than the zinc 2 positive, yes, only 4 rather than 6 and 8 sulfur ion can be pegged around the zinc atom. Yeah, it's true. Now they are the coordinated with the 4 atom, and it's not about the size of the atom, but it's about the coordination number, the how they are the arranged one. I mean, if as this coordination number, it is not I mean here it is no, here also the zinc ion, and it's also the zinc 2 positive ion. It's not about the state of the zinc positive or negative ion one. Okay, so this is the correct. Yeah, it will be the coordinated with the 4 sulfide ion. Now the zinc sulfide has the mixed covalent and the ionic character one. Zinc sulfide is the ionic one, Zn2 positive and the 2 negative, they are the ionic one. They are not having the covalent. Covalent is basically the overlapping of the orbital one. So this is not having the covalent one. So this is not correct. So A and C will be the correct answer for the ZNS one. ZNS. Okay. So this is about the question number 6. Is it clear for everyone? Okay, I am assuming it is clear. Okay. Okay, then is it clear? So let's move to the next question, question number 7. Now, in question number 7, it is asked M2X having a structure closely related to the fluoride one, that is CaF2, that is the inverse fluoride, because the fluoride having the structure of MX2, so inverse is having the M2. X1 structure, hence it is called as the anti-fluoride structure. Yes, true. Now in such a structure, X now A part X form the FCC lattice, while all the cation occupy the tetrahedral void. The coordination number of the X is the eightfold. M formed in the C part, M form the FCC lattice, while X occupy the tetrahedral interstices, and the D is the lattice type is the FCC one. So the what is the interfluoride structure one? Interfluoride is basically your opposite to the MX2, but here the thing is that the in whatever the position of the cation in the fluoride one, that will be the same for the anion here, and the whatever the position for the anion here, that will be the same for the cation one. I mean, they will change their position, they will exchange their position in cation and the anion one. In cation, so the this MX1, this is the O negative will be the X will be the your FCC lattice one, and your M will occupy the tetrahedral interstices one. Okay. So this one, or it is having, or I have, it is having the closely packed structure of, closely packed of O2 negative ions. The ion O2 negative that will occupy at the FCC lattice like structure, because the ion will present at the corner as well as the face center of the unit cell. And the sodium, there is the sodium here. The example of the antifluoride is given as the N2O. So the my O will occupy the FCC like structure, and my the Na positive will occupy the octahedral interstices one. And the no, the octahedral, the tetrahedral interstices one. And each Na positive, because they are this Na positive having the stoichiometry is like this, N2O. So this they having the, because in the fluoride we have seen the coordination number is, in the last question we have discussed, that is the coordination number is the 8:4 here. So but the in the end I mean in entafluoride they have the coordination number is 4:81, and your each Na positive ion will be surrounded by the 4 oxygen atom, and the this will each O2 negative will be the occupied with the 8 one, because you have to take care of stoichiometry of the this one Na2 one, because 8 having, so this will okay, this Na positive will be the connected to the 4 O2 negative ion, and the each O2 negative ion is surrounded with the 8 Na positive ion one. So, so this is about the anti-fluoride structure. Now let's come to the A part. A's part in the X will form the FCC lattice. Yes, X will form the FCC lattice, while the all the cation occupy the tetrahedral voids. Not the all the cation, but it will occupy the tetrahedral one. But most interstices are not the all the void that are present, but it the interstices. But there are the some specific one, because we have to follow the stoichiometry also. It will only occupy the sum of the one, so that they can maintain their stoichiometry. So this is only occupy the tetrahedral interstices one. The coordination number of the X is the eightfold. Yes, coordination number of the X will be the 8 one. This is true. And the X M form the FCC lattice, while X occupy the interstices one. Here this is okay, M2X. No, X will be the X will form the FCC lattice, and the M will the octahedral interstices. This will be the interstices, not the void one. So A will be the, and the third D part is the lattice type is the FCC. Yes, here the lattice type is the lattice. But this the FCC one. Okay, so remember these are the different thing, because you can see from here there FCC we have the one, we have the two type, both are having the FCC lattice one, but there the motif are the different one. In the fluoride case they have the this I mean if they have taken the example of CaF2, where this is, or I can say this is the my mx2. So my x will take the position of 0 0 1 by 2 0 0, and the my m will take at the 1 by 4 1 by 4 1 by 4. In the anti-fluoride they are having my a atom, this is my a atom will occupy the 0 0 1 by 2 1 by 2, because here you can see they also their position are exchanged. Here this m, whatever they are having in the for the this one for the m, now they are having for the x1. Okay, m now it is for the m here, now it's having the for the x1, so they have interchanged their position one. So the interfer in anti-fluoride one, the motif for the a will be the, this is for a to x1. So a will be the 0 0 0 1 by 2 0 0, and for the x will be the 1 by 4 1 by 4 1 by 4. So each of them are having the FCC lattice. So lattice type will be the FCC one. Okay, so this B, D and A will be the correct answer for this one. Okay, so this is all about the question number 7. Okay, let's move to the question number 8. Just read the question and just tell me what will be the, this is the easy one, so you have to tell me what will be the answer for the, a compound formed by the elements A and B crystallize in the cubic structure in which atom of A are at the corner and the while of that of the B are at the face center. What is the formula of the compound is? So now you have to tell me A and B both are crystallized in the cubic structure, but A occupy the position of the at the corner of the unit cell, but B are at the face center. So what will be the formula of the compound one? So what will be the compound for this one? If A and B crystallize in the cubic one, and in which atom of A are at the corner while the B are at the face center, what is the formula of the compound? Now AB3 I think. Yeah, it will be the AB3. How you calculate this one? First you have to find out then how many number of the atoms, effective number of atom in that unit set particular one, and then you have to arrange in the stoichiometric coefficient. Core, yeah, I mean I didn't get your point. Sorry. Yeah. Okay. Yeah, it will be the AB3. I mean, I didn't get what is the wrong in this part. I mean, okay. Let's discuss this one. So, how they will first effective number of okay. Okay, fine. So the compound formed by A and B. So first we have, because A atom are occupying at the corner of the unit cell. So number of the effective number of, we can say the number of A atom will be the effective in the unit cell will be the 1, because eight atom will at the corner, and the what will be the effective I mean fraction for the to the 1 unit cell of the, at the corner when the atom are sitting at the corner, that is the 1 by 8. So this is giving the 1 atom for the, this is for the A, and if your atom are sitting at the face center for the B atom, and at the face center the total number of atom will be the 6, the contribution of the face center atom will be the 1 by 2, so it is giving you 3. So what will be the A ratio B, that is giving you the 1 ratio 1, I mean the 3 corresponding to 1 atom, corresponding to the 1 atom there are the 3 B atom. If I'm where my A atom is only corner, but my B are 3 atom are there on unit cell, so the my compound will be the, don't think you have to cross multiply it here, it is not like that, corresponding to 1 atom, because A there is only 1 atom in the unit cell, and the B atom you are having the 3, for the same unit cell you are having the B3 atom for the B atom, so the compound formula will be the AB31. Okay, so A will be the right answer for this one. So this is all about the question number 8. Now let's move to the question number 9 one. So rutile has the following characteristic. In A, it is useful in the polarization optics. It is made of the TiO2. It has a hexagonal unit cell. It has a tetragonal unit cell. So if you know that this is rutile, or we say the rutile or NTAS, both are the form of the TiO2, that is the titanium oxide. B, yeah, it is made of the TiO2. And what about the other parts? I mean, in ABC, does any ABC, ACD will fulfill this condition? I mean, does they are the characteristic of the rutile one? Yeah, B is the correct one. What about A and C and D? How they are arranged in the rutile and the NTAS phase? Let's discuss. In the rutile, the my atoms are arranged, they have the structure of the tetragonal one. But in the NTAS one, also they are having the tetragonal one, but they are stable, they are less stable one. Rutile is the more stable at the higher temperature, and this is at the stabilized at the lower temperature one. These are the correct experiments. Some I'm just letting you know. B and D. Yeah, this is the tetragonal with the and the, because it is having the higher density also. So higher density. So it will be the higher refraction index compared to the entire one, and also they having the strong photocatalytic activity. And this is also this rutile part is TiO2 is mostly used in the optics part, mostly used. So it is also, so it is just a second. Okay, so this is photocatalytic activities. So this rutile TiO2 is mostly used for the higher temperature, and the for the, because of the high refractive index, it is also used in the polarization optic. So A will be the also the correct answer. They having the low photocatalytic, because the this enters having the photocatalytic one property is this one. Okay, so A, B, and D will be the right answer for the, can the TiO2 used as a dielectric? Yeah, TiO2 generally BT we consider as a dielectric matter. For the BT consideration, we took the TiO2 because they are having the high refractive index, and the dielectric constant also for the this TiO2 is also high. So we can use TiO2 for the dielectric material. Okay, so let's move to the next question. Question number 10. In the 10th, this the perovskite unit cell is shown here, consists of the calcium, oxygen, and the titanium atom. The formula of the this perovskite would be this TaTiO2, TaTiO3, and this is not the Ta, sorry, calcium, I mean CaTiO2, CaTiO3, CaTiO6, CaTiO4. CCTO. Yeah, B is the correct answer. Okay, B is the correct answer, because if you count, because the here these are atom at the are the calcium one. If I'm calculating the number of the effective number of the calcium atom in the unit cell, because they are at the only at the center, only at the corner of the Q1. So the this having the one atom. C, yes, CO. Yes, this will be the C plus CO2. Yeah, if the formula it is asked, you can see also the here also, because the all the atom calcium are at the corner of the unit cell. The number corresponding to Ca will be the one. For the this titanium is at the body center, so it was also having the one effective number, and the oxygen are at the face center one, so that will give you the 1 by 2 into 6. That is also having the 3. So this having the formula CaTiO31. So B will be the right answer for this one. Okay, this is the easy one. So let's move to the next question, that is the question number 11. Now this is the figure that is given here, and maybe you probably know about this figure. What is this? But you have to tell me. So this O2 negative ion have the BCC arrangement, FCC arrangement, primitive cubic arrangement, or the HCP arrangement one. Here this I mean the shaded one having the this atom is having the this atom is basically your A2 positive, B atom are of these type. You can see the dark color, I mean the black one are the B3 positive, and the O are the that the not shaded one complete the only the these are the O2 negative ions. So from this one, from this figure, you have to tell me the O2 negative ions have the BCC arrangement, FCC arrangement, or the primitive cubic arrangement, or the FCC arrangement. So which of the following having the O2 negative ion? First look at the O2 negative, where are they sitting in this structure one. Then you have to tell me. So you know about the BCC arrangement, FCC one, primitive cubic arrangement, and the HCP arrangement. By looking at the O2 negative ions from this one, you can find out which arrangement the O2 negative ions are following one. If you see from here, this one O2 negative ion, these are atoms are present at the, if I'm seeing this one, this is having the, this at the corner of the this lattice one, and the also at the face center one. This is also for this outer part, this for this one, later one this one, and they are also at the I mean the are the corner of the lattice and at the face center of the one. So my O2 negative ions will have the FCC arrangement. So my B will be the correct answer for this one. In the next part also, for the same thing we have to calculate for the I mean, okay, if the this is if somebody asks you what is the arrangement for the B3 positive ion and the A2 positive ion, so what will be the arrangement for the B3 positive and the A2 positive ion? Your B3 positive ion are situated at the A center, and the this A2 positive are at the tetrahedral position one. So what will be the arrangement for the this B3 positive and the A2 positive? That's also asked in the next question. If I move to the question number 12, they are having what will be the site represented by the B3 positive ion and the A2 positive ion? Your B3 positive ion are at the A center, and if I look at this A2 positive, that is my tetrahedral connected to the 4 atom. So my this A2 positive will be connected to the my tetra tetrahedral, and this is A center, so this will occupy the octahedral position. So the what will be the right answer for this one? If I see the site represented by the B3 positive and the A2 positive ion R will be the, for the A2 positive will be the tetrahedral, for the B1 it will be the octahedral, and the O2 negative it will be the FCC structure one. So for B2 B3 positive it will be the octahedral, and the A2 positive, it will be the tetrahedral. So B will be the correct answer. Yeah, B will be the correct answer. No, B will be the not the tetra and the octa. You can see from here. This, if I'm taking, I mean, these are this B atom. This is the B atom. If I say this is connected to the octahedral, this is connected. This is in the same plane, and one atom will be the here also. This is connected to here from this one and this one, this one and this one. These are octahedral connected to the O2 positive ion. Yes, ma'am. Okay, okay. Huh. So this your B will be the octahedral, and this A positive, A2 positive will be the, it is connected to the 4 oxygen ion, so it is the tetrahedral connected one. Okay, so let's move to the next question, the question number 13. So the same, what will be the formula of the compound, this one? For this one, it is complicated because we have the 2 unit cell. So if you can see from this is the compound formula of the, this is for the standard one. Maybe you know the C part. C, what will be the C? Yeah, it will be the Ab2O4. This is the spinel one. And this spinel, you have the 2 types, that is the normal spinel and one is the inverse spinel. And they are having the structure of Ab2O4 in the normal structure, in the normal spinel. This, if this is the Q, if I'm taking oxygen and the my B atom, that are the my octahedrally, B atom at the octahedral site and my A atom at the tetrahedral site. You can see from here also, this your atom is the tetrahedral, and these are these are diagonally positioned is this one. And if you see from here also, because they are not here and not here, these are the diagonally one situated, and the in this one, these atoms are the B atom are the octahedral side from this one, or you can see from this is the octahedral, it is connected. If this is this one, it will connect to the octahedral one. Same thing, one here, 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 and one will be the here from one, and this one, this will connect to the octahedral one. So this the ratio will be the tetrahedrally 1/4. If oxygen will be the my one atom, and that if I'm take the A1, this will be the 1/4, and this will give you the octahedrally will. Okay, let's don't confuse with this way. So the formula for this compound will be the Ab2O4, and this is my the spinel structure, where my oxygen ion at the FCC F6 like structure anion, and the B are the octahedrally and the A are the tetrahedral, and the in the inverse spinel we have the B, that is my tetrahedral I guess, and the AB are at the octahedral, and your oxygen is the anion occupying at the FCC lattice one. Oxygen O atom will form the F61 closely packed structure one. So this is all about the spinel structure. Okay, now let's move to the question number 14. So what will be the coordination of Ti, Ti4 positive and O2 negative in the rutile structure R? We have already told you that are also that are existing in the tetragonal one. So you have to tell me this is TiO2. So what will be the coordination of the Ti4 positive and the O2 negative one? And they are existing in the tetragonal structure one. So what will be the structure for the coordination number for the one? Okay, let's see first. See the structure of the TiO2. This my Ti atom, Rs at the corner of the cube, and OX and this is also the body one, and this oxygen atom are the tetragonally connected to this one. If you see this one, this one, this one. So what will be the coordination number for the TiO2? I mean coordination of the titanium. If you see the rutile structure of this TiO2, this is the crystal structure TiO2. This is the titanium one. Blue is the titanium. Red one is the oxygen one. So what will be the coordination number of Ti? From the figure you can see what will be the coordination of the Ti and the O2 negative. This is also O and this is also Ti. So what will be the coordination number for this oxygen and the titanium one? Yeah, A part. For the titanium, it is connected to the 6 one. Yeah, the coordination for the titanium it will be the 6, and for the oxygen, because oxygen is connected to the 3 titanium atom, and because of they have the stoichiometry like this, so they will be connected. It is connected to the 3 of the, if you can this cation, because we calculate the this radius ratio for the cation, and for the anions we calculate according to the stoichiometry concept, stoichiometry. So my this titanium 4 is also here existing, having the coordination number of 6, but stoichiometry they have the in the 1:2, and they have to maintain this thing. So what will be the coordination number for the O will be the 3, otherwise they won't be equal. So the coordination number for the oxygen will be the 3. So the right answer for the coordination number of the titanium 4 positive and the O2 negative will be the 6 and 3. A part will be the correct one. Okay. Okay, let's move to the next question. That is the question number 15. So this in question number 16, a unit cell of the ReO3 consists of the cubic arrangement of the Re atom with the oxygen atom centered along the each edge of the cube. The coordination number of each Re atom. Here there is existing a ReO3. They having the structure having the AB, the perovskite one, but not having the A atom. This is the BO3, or here my B is the Re, sorry, of the cubic, consists of the cubic arrangement of your Re atom. This is having the cubic arrangement with the oxygen atom centered along the each edge of the one. So your oxygen atom are arranged at the each of the cube one. So what will be the coordination number for the each Re atom one? So what will be the coordination number one? So if you see, yeah, it is correct. A will be the correct answer. So how it will be? If you see, then this is Re3. This is the crystal structure of the ReO3. And here my Re, this is my Re atom arranged as it is already told. This is the cubic arrangement of the Re atom. Yes, my Re atom are the cubically arranged, are situated at the corner of the cube and the octahedral void position. Yeah, octahedral, it is the octahedral void position. This atom is arranged in such a way. So the coordination number is a 6. And my oxygen atom, this is along at the each edge of the cube. So here these are red one are my oxygen atom. If you see this cube will connect it to the other 8 1. So the coordination number for this one will be the Re will be the 6 1. So what will be the coordination number for the oxygen one? I mean 4 in a plane, one above and the one below. Yeah, this is true. There's a 4 atom will be in the one plane, because this one cube unit cell will connect it to the one unit cell that is above here. This is from, I mean, front of this unit cell, and the parallel to this one and the back of this one. This is connected to 4 and above one also. So if you see this one, this Re atom will be the octahedrally connected one. So the coordination number for the Re will be the 6 1. So what about the coordination number of the O, oxygen one? Coordination number of the with respect to Re will be the 2. Yeah, the coordination will be the 2, because you can see also here this oxygen atom is only connected to these two atom only. So the coordination number for the oxygen will be the 2, 1. So if you know the crystal structure of any atom, then you can tell about the coordination number and how they are, position in that unit cell, what type of the arrangement they are following. So you can easily calculate. So at least remember for the standard structure, cubic structure, so that you can find out. So what will be the coordination number? Otherwise, you can also remember if you have the idea of the radius ratio, and you can correlate with this coordination number. That will also give you a good idea of the coordination number 1. So this is the about the question number 15. Let's move to the question number 16. So in the question number 16, if the radius of the cation, that is the radius of the cation m, having the 0.54 angstrom, and the anion, radius of the anion, this is x, this is 0.92 angstrom. So what will be the solid made by mx? There is some solid. So what will be the coordination of the cation is likely? So you have to calculate the coordination number of cation. So how you will calculate the coordination number of the cation? Yeah, will it be the octahedral? So for taking the radius ratio. So yeah, first you have to take the radius ratio. If the radius is given, so you have to, because we know the relation between the radius ratio and the coordination number. So first calculate the radius ratio. That is the radius ratio. Then compare with the type of the STR. STR. Then is what do you mean by the STR? Is it so? Radius will be the radius of the cation and divided by the radius of the anion. First you have to calculate the radius ratio. Now substitute the value. This will is a 0.54 divided by 0.92. So this will give you value of, if you divide 0.54 divided by 0.92, what will be the value of the radius ratio? So it will come out, oh, this is the ratio of 0.414. Okay, so if they are the 0.14, because we have already discussed what if the what will be the range for this range. If we have, this is around, we are getting around the 0.141, 141 approximately. So this atom are lying in this one. Is it lying in this range or this? Because 0.414 is having the, this is at the boundary point. So you just calculated the accurately, so that we can differentiate the what will be the coordination number for the this atom mx1. So this ratio is coming out, how much it is? This is, let me calculate. This is 0.54 divided by 0.92. So this is coming around the 0.58. This is not the 0.04, 0.5869. This is the dimensionless quantity, because it is the ratio of the two radius. So your radius will be the cancel out. So this is lying, the value of this one, this is 0.7869. So it is lying between the 0.4142 to 0.725, I guess. Let me check. Yeah, this is lying at the 0.4142 to 0.732. So the coordination number will be the 6, and it will be the octahedrali connected one. So if you go, so this for this one, the coordination number, this is lying in the range of 0.41 to 0.732. So the coordination number will be the 6 and it is octahedrally. So the coordination of the cation will be the B. So the octahedral, not the tetrahedral will give you the for 4 cubic if the coordination is coming around the 8 and triangular is having the coordination about the 3 one. So and this is for the 6 one. So we are getting around the coordination number 6 one. So the octahedral, the coordination of the cation will be the octahedrally one. Okay, this is about, and we have also list for there is list. Let me show you if I have, just a second, let me check it. Does I add it there or not? Okay, I have. Okay, for this is we have also predicted an actual coordinated this one, that is also professor has also told you, because the in the we for the CF2 there is we can have the, because they are lying at the boundary one, they can have the octahedrally also coordination of the predicted coordination number from the radius ratio octahedrally or cubic they can occupy, but they are the actual coordination number one way with the cubic one. And this is another one example that is opposite, that the SiO2. For the SiO2 same, they have the Rc divided by the Ra, that is your radius ratio is around 0.20. So they can have the threefold as well as the or the fourfold symmetry, but they are occupying the fourfold coordination number. So these are a few exception, otherwise all atom otherwise follow the radius ratio rule. Okay, so this is the, sorry, so this is about the radius ratio. Let's move to the next question. A part, no, yeah, now it's correct, I guess. B part, na, is it clear na? The question number 16, is it clear? A or B? Dinesh, I think you are confused, I mean. Is it clear to you which one is the tetrahedral, the octahedral? If we take the radius of the if we divide the radius of cation divided by the radius of anion, it will give you 0.54 divided by 0.92. It is giving you value the around the 0.5869. That is lying within the range of 0.414 to 0.732. So this is giving the coordination number of 6. This is the coordination of 6 will be the octahedrally connected one. So the B part will be the right answer for this one. Okay. Let's move to the next question. I think it is clear now. That's the question number 16. Is it clear? Is it clear, question number 16? Okay, okay. So let's move to the next question. That is the question number 17. In ABX3, that the perovskite structure ABX3, the position of A and the B atom position are. A and B atom position are. What will be the position of the A and B atom? So this is your ABO3. I mean AB3, where A is your green atom, B is your, that is at the center of this cube one, and that is octahedrally connected one, and C is the atom that are at the face center of the unit cell. So these are the, this is the ABC structure. So what will be the position of A and B? You have to tell me the position of the A and B atom. B. Yeah, B will be the right answer. So the position atom, because your this A atom are at the corner of the Q1. So the what will be the motive for this one? Because these are only the corner ones. So the motive for the A1 will be the 0, 0, 0. Okay, and for the this, if I am talking about the B atom, because B atom at the center of this cube one. So B atom, the motive for the B will be the atom, because it at the center one. So it will be the 1 by 2, 1 by 2 and the 1 by 2. And what about the C atom? If I have to calculate the C atom, so what will be the motive for the C atom? Because you have to remember for the motive for the all the atom A, B, C. Here it is asked only about A and B. So for the A and B, for the oxygen one, it is flying at the phase center. So the motive will be the 1 by 2, 0, 1 by 2, 1 by 2, 1 by 2, 0, and the 0, 1 by 2, 1 by 2. This is for the oxygen atom. For so the in perovskite A is having the at the 0, 0, B is having at the 1 by 2, 1 by 2, and the oxygen is at the 1 by 2, 0, 1 by 2, 1 by 2, 1 by 2, 0, or 0, 1 by 2. So according to this, we have to tell the about the A and B atom. So for A, it will be the 0, 0, and the for the B, it will be the 1 by 2 and the 1 by 2 and 1 by 2. So your B will be the right answer for the perovskite one. This AB atom position will be at the 0, 0, 0, 1 by 2, 1 by 2 and 1 by 2. This is about the perovskite. So we have discussed, a few ionic solid one. For the these are the standard one. At least you have to remember the standard structure. The standard crystal structure of the material, so that you can easily check the position and the coordination number. So this will be the next question. Okay, now the you have to find again the you have to find the what is the coordination number of the cation in O atom given the ionic radius of A2 positive and the O2 negative are the 76 and the 140 picometer respectively. BaTiO3. Yeah, this is the this is perovskite R is the BaTiO3, and we also discussed the calcium titanate, also the magnesium titanate. This A atom is your divalent. Yeah, this is of the perovskite category. STR is basically what is STR meaning? Structure. Okay, structure. You are representing the perovskite structure. Okay, fine. This is A is your divalent cation, and here B in AbO3. B is the your trivalent cation. So AbO3 is the this barium titanate, calcium titanate, magnesium titanate. All are of the perovskite, all are of having the perovskite structure. And there are the some neobate also, the neobate also having the this is neobate having the some neobate that the I guess, but the formula of the Mg and B, this is Mb2O5. No, this is not the one. There are neobate also that also occupy that also occupy that perovskite structure also. This neobate zirconium something GnBO3 something like that. There are the neobate also titanium as well as the titanium neobate, or they occupy the perovskite structure in the form of AbO3 one. In the question number 18, now this kind of the question, yeah, this type of the question we have already done. The now we have to calculate the coordination of the cation in AO atom. So the ionic radius of the this A2 positive and in the 76, O2 negative is the 120. This is the 76 picometer. This is the 140 picometer. So you have to calculate the coordination number. Again, you have to calculate the radius ratio. That is, the radius ratio will be the radius of the cation, that is the 76, divided by the radius of the anion, that is the 140. So if you calculate, so it will come out around the 76 divided by 140. So this will give you 76 divided by 140. It will give you around 0.5428. Okay, this is giving you around the 54. Now you have the this compound having where the cesiums are they are having this of the okay, not the this range. If you these are the some I have already told you, this is having this cesium fluoride and this silicon dioxide. They are having, because they are at lying at the boundary, so they occupy the actual they can predictive coordination number can be the octahedral than the cubic one, but they actually the coordination number of the cation is the cubic one. For the this one, for the SiO2, the radius ratio is 0.2. The predicted coordination number is the threefold or the fourfold, but the actually coordination number is the four 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 one. For this one, if I check this one, so the radius ratio is coming out the 0.5. This is 5. I mean 0.5428. So this is lying in the range of 0.4142 to 0.732. So this is for the this range. The coordination number will be the coordination number will be the 6, and they are the octahedrali connected. Okay, so this is about the question number 18. And so if someone has any doubt in any of the question in the assignment number 5, then you can ask. Yeah, the coordination number for the octahedral will be the 6. Yes, it will be the 6 one. So this is all about the assignment number 5. Done, ma'am. Yeah. Then so if you have any query, then we can discuss. I mean, otherwise I will summarize the assignment number 5 from the starting, and then we will end up this meeting. But if you have any query till this point, then you can ask. Can we develop the stoichiometric compound out of two perovskite structure? I mean, for the perovskite structure, the stoichiometric compound for the perovskite structure, if I say, let me check it. I mean, will it this work for this one or not? This A atom will add the one, this B atom will also the one, and this, yeah, it's also working for the perovskite one also as well, because see, if we have the this atom na in the perovskite, this is, let's say this is my unit cell. This is my E atom is presented here. B atom is my presented at 0, because they have the motif as like A is at the 0 0 0, B as the 1 by 2 1 by 2 1 by 2. Okay, experimentally, I mean the okay, you want to say this is if you have the barium titanate BaTiO3 plus calcium titanate TiO3. So this is giving the barium titanate CaTi2O6. Is it true? Okay, so uh, thing is that you have to check first thing, does it, yeah, it will be the neutral one, because we have to check there are the three condition, I mean the for the poly condition we have discussed in the last car, it should be the stable for the this one. If the all are equal for the Ni, please convey, please convey this doubt to sir. Okay. So what you can we develop the stoichiometric compound out of two perovskite? So you want to develop for the stoichiometric coefficient for this barium, calcium, titanate. I mean this one. I'm asking. I mean, so if this is the because this the perovskite having the structure of AbO3. This you are asking is not in the term of AbO3. It should be something B and ACS should give you the total one. The one, and it should be the titanium one element and the O3. This, if let's say this is barium zero point 0.5 and the calcium zero point 0.5. If these are, this is giving you, this is you giving the perovskite structure one. It should be in the AbO3 structure. This is one example to know in general. But it is possible or not? I mean, can you unmute, sir? I mean, so that I can, I mean, I can get the clear. I mean, what is the purpose? I mean, what is the doubt? I mean, if you two are combining the two perovskite, one is already perovskite, another is also perovskite one. If you combine them, they are also making another perovskite structure. You are telling that, and you have to find out the what will be the stoichiometry. Okay, so this thing we all in the research part when we have to only consider this stoichiometry, and they were experimentally they will I mean if you want to make that compound that it can easily make, but it should be in the form of like AbO3. It is something A dash B2O3. There should be this cation should be have the at the substitution of the tetrahedral, because this my A is having at the tetrahedral one na? This is at the A side this, so the some of the when we are combining, so some of the cation, this cation should go into the sum of the site of the barium. It will occupy, and there will be the some deficiency, there will be the some occupancy, or there will be the some lattice strings, because depend upon the ions ion size and all that. If you want to I mean this, if we have, you want to combine, let's say this is my Ba titanium oxide plus Ca titanium oxide 1, and you want to make something A, that's let's to be Ba, let's say 0.2 calcium point, it should be total should be the one, and the titanium oxide, this one. This can easily experimentally done. I mean, we can mix these two and can get this one. This is also the another perovskite one. We have to only consider the stoichiometric coefficient of 0.2 and the 0.8. We have to balance this equation. For this, if I'm want to I mean synthesize this by, yeah, powder metallurgy route, by the powder metallurgy route we can synthesize this one. We have to only consider the this stoichiometry only. We have to take care of the stoichiometry, how much we are barium titanate and how much the calcium titanate we are taking for this one. For this one, if this B and Ca both are going at the A side, so the barium should be at the 0.2. If I'm whatever the zero point 0.2 mole of the barium titanate will combine with the zero point 0.8. how to calculate any reference? Sir, it will, if you are calculating this, I mean, for the any, I mean, you can check any paper in the in the powder metallurgy route. You will find any. I mean, if you take the, because similarly, if you, let's say this is the barium titanate, you want to how we will make the barium titanate. This is the barium titanate. Basically, make the barium carbonate. This is barium carbonate by the titanium oxide. This will give you the BaTiO31. So how we make the this perovskite one? This is because of these two and these two, and we take the stoichiometry coefficient. We balance this equation. Balancing the stoichiometry coefficient, we can make the BaTiO3. So barium should be the one here, the barium, and titanium should be the one. Yes, the titanium oxide also of the one more. The oxygen are the three here, but if I see here, the oxygen atom are the five. Total oxygen atom are the five, and we have the carbon also. So it will release my the carbon plus 2 oxygen. So this equation is my balance equation now. So we can take the 1 mole of the barium carbonate plus 1 mole of the titanium oxide, that will give you the 1 mole of the barium titanate plus the CO2 that will release here. So similarly, if you want to make something this like the barium titanate plus the calcium titanate, you can make this one Ba whatever this is X or the CaY TiO3, and this will either the oxygen or will be the sum. This that will I mean you can form. Either you can take the product already made product, or you can take the initial one, the raw material, that's the barium carbonate or the titanium oxide or the calcium oxide one. From there also you can make. I mean, either you can tell me the what stoichiometric coefficient do you want to compose, I mean synthesize, so that I can tell you how much the mole of barium titanate or the this calcium titanate will be the combined with that one. It will be the X will this one or the Y mole of the calcium titanate one. It will be something like that. X mole of the barium titanate will combine with the Y mole of the calcium titanate, and it will go like this way. Barium XCO X and the CaY titanium oxide one. Okay, okay. I mean, it will be something you have to only balance the equation. Once you balance the equation, you can synthesize experimentally. Powder one is the so easy. You have to take only consider the stoichiometry one. Okay, fine. So this is all about the assignment. Now this is all about the assignment 5. Let me summarize from the first question and then we will end up this meeting. So for in the first question, it is asked the fraction of the octahedral void filled by the aluminium 3 positive ion in the alumina is. So we know that the alumina is having the this O2 negatives occupy the hexagonal lattice, and Al3 will the octahedral, and each octa of this HCP having the 2 octahedral voids per unit cell or the 1 octahedral per atom. So we have the 3 oxygen ions, so we have available 3 octahedral ions, but this stoichiometry for the 3 oxygen atom we have the only 2 aluminium ion are only occupied. So my 2 octahedral voids will be the field. We have the available 3 one, but what will be the fraction one? The available are the 3 one and the occupied are the 2 ones. So when we divide this one, so we will get the how much the fraction of the tetrahedral void will be the filled by the aluminium 3 positive one. In next question, what is the main length constant for the NaCl? For the standard crystal, we have already, I just here mention it here. For the cesium chloride 1.73, NaCl it the 1.78, fluoride, zinc sulfide, virgilite is it is given here. So you have to remember for this one, the for the main length constant one. This main length constant defined as if when we calculate the potential energy of the any I mean the potential energy of a single ion in a crystal. If we have to calculate the single ion, we consider the other atom at the point charge and their distance and their charges also. From there we calculate this Planck constant one, and this is also represent the lattice energy of the your crystal structure also. In question number 3 we have if the radius ratio that is lying in this region, what will be the coordination number? So we have the relation between the radius ratio to the coordination number. Once we know in which range it is lying the radius ratio, then we can calculate the coordination number, corresponding coordination number for that one. For it is given, because for it is, if it is less than 0.155, the coordination number will be the 2. If it is lying at the 0.155 to 0.225, the coordination number will be 3. And if it is lying at the 0.225 and it is 0.414, the coordination number will be the 4. And if it is lying in the 0.414, 0.73, the coordination number will be the 6. And if it is 0.73 to 1, the 8 cubic one. And if it is greater than 1, when your this cation is bigger than your anion, so there the coordination number will be the 12. That will be the closely packed, the hexagonal closely packed one. And if fluoride having the coordination number 8:4, so which of the fluoride having the structure? So these atoms having the fluoride structure, and the antifluoride we have already, the coordination ratio is the 4:8, because they interchange their position in cation and the anion one. In question number 5, we have discussed about the NaCl structure. So what are the NaCl structure? Your this Cl anion occupy the FCC structure, and this Na positive are occupy this octahedral position. So there is no tetrahedral position are occupied, only the octahedral, all octahedral position are the occupied one. In the next question, this is about the zinc sulfide. So what are the zinc sulfide? In the zinc sulfide, zinc is occupying the FCC lattice, and the zinc positive is the tetrahedrally connected to the sulfur atom. So this is all the, and this is the zinc sulfide is the your anionic one, and it is having the structure, same structure like the diamond one. In question number 7th, it is having the anti-fluoride one, and you have to tell the coordination number, as we have already discussed. For the fluoride, the coordination number is the, for the cation and anion will be the 8:4, anti-fluoride will be the 4:81, and they also have the X will occupy the your FCC lattice, because both are having the FCC lattice one. So in question number 8, now they have, I already told you where the your atom are sitting, so you have to find out the formula. So if A and B are at the, you can find out how much atom, the effective number of atom in that unit cell, you can easily calculate. Either you can find it here, or you can visualize this when the atom are present, they are there, what can be the structure, because we have the some standard structure. From there you can compare, and you can find out this is having the AB3 structure, or if you say having the perovskite structure where AbO3, but A is not present in the BO3 one. Okay, in the next question, there, this is the characteristic of the rutile one, that is the TiO2. That is, we have already discussed the rutile and the enters phase. Rutile and the enters phase both have the tetragonal, but rutile having the higher density and the higher refractive index, but the low photocatalytic activity, and that it is also the most stable. This enters phase is stable at the lower temperature, and it is not more stable compared to the rutile one, if I say. So it is, this rutile TiO2 is used for the higher temperature and the polarization optics, and it is having the tetragonal unit cell. In the test question, this is the all about the AbO3 structure. We have in the FCC, in this later, this is the spinel structure, that where is Ab2O4, how the your oxygen ion are arranged. This are having the FCC arrangement. B3 positive are the your octahedrally arranged, and the A positive are the your tetrahedrally arranged. How the atom are arranged in the spinel structure, it is discussed in question number 11, 12, as well as the in the 13. In the 14, we have discussed the coordination number of the TiO2 rutile structure. What will be the coordination? We have to also consider the stoichiometric coefficient of the in the element, and the coordination number. Once you find out the coordination number of the cation, you can find out for corresponding for the anion one. In the 15, the same, the coordination number you have to calculate. And the 16 also, we coordination number again. Now the here you have to calculate with the radius ratio, there you have to calculate with the crystal structure. In 17, what will be the motif of the A and the B atom in the perovskite one? A atom having at the 0 0, B atom at the body diagonal, that is B 1 by 2 1 by 2, and the O oxygen is at the 1 by 2 0 1 by 2 0 1 by 2, 0 1 by 2 1 by 2, that is having at the face center, and the 1 by 2 1 by 2 0. This is the motif for the A, B and O atom. In the A10, again you have the coordination number. You have to find out the coordination number. Ionic radius for the cation as well as that anion is given. You just find out the radius ratio and compare with the given the range for the radius ratio and the corresponding coordination number. This is all about the assignment number 5. If someone have any doubt, then we can discuss. Otherwise, we will end up this meeting one. Does anyone have the any doubt till this point? I mean, in the assignment 5 or anything? No doubt. Okay, sir. Then we will end up this meeting. Thank you. Thank you, sir. Does the Kalpana, do you have any doubt? Kalpana and the Jakar, do you have any doubt? Okay, no, thank you. And the Kalpana, what about you, Kalpana? Do you have any doubt? See, I don't think so. She's here. So we can end up this meeting. Uh, uh, if we can end up this meeting, or we can discuss the next assignment. In the we will discuss this ionic solid part is completed by this week. This completed in this week, and we will in the next week we will discuss about the non-crystalline. Here up to this point we have discussed about the crystalline solids one. Now we will discuss about the non-crystalline. The next assignment will based on the non-crystalline solid, and I think you have the midterm in between also. And in the next week we will discuss about the structure determination and this imperfection in the solid one. So there are the 3 units that are the left here. One is the non-crystalline structure, and the another one is the imperfection in the solid one, and the deformation, I guess the deformation or something, the structure determination, the structure determination of one. So uh, we will continue our next assignment with the non-crystalline solid one. And till that point, if you have any doubt, you can ask in the discussion form, or you can mail me. We can respond you accordingly. Thank you.